Hello, today we're looking at section 13.9, applications of extrema of functions of two variables. There's just one objective, and that is to solve optimization problems. So this is very similar to solving optimization problems in AP Calculus AB, for example. So to me, it's one of the most rewarding things we can do. The advantage also is that there's no new material. We are just using what we've learned in particular in section 13.8 and applying it to exercises. So we have two examples here. The first one is mathematical. The other one is maybe a little bit more real life style. Let's look at the first one. So we have a rectangular box resting on the xy plane, and one of the vertices is at the origin. Then the opposite vertex is here, and that one has a condition on it. It is lying in the plane 6x plus 4y plus 3z equals 24. So this figure shows the situation very well. You can move that point anywhere inside along this yellow triangle, and you can see how it's going to change the size of the box. Maybe it's going to be tall and thin, or maybe it's going to be wider but not as high. And of course, the question is which one of these boxes has maximum volume. Had the question been what box has the minimum volume, then we may realize that if I pick this point along any of the edges of the triangle, then the box would have a volume of 0, and that would be the minimum. So it's a more open question to find the maximum. When we solve such exercises, we are going to have to focus on the inside region and on the boundary. We need to do these two things separately, and they require different tools. Firstly, let's set up the equation for the volume of the box, v equals x times y times z, and we can substitute z because we know that we can solve z here, and we can find that z equals 8 minus 2x minus 4 over 3y. So in the end, our volume is a function of two variables, x and y. So the domain of this function is in the xy plane, and it's the triangle like here. If you look at this sketch, we are talking about this triangle here in the xy plane. If I choose x and y here, then the height of the box is defined, and the box itself is defined. The volume is defined. So let's start with the boundaries. What are the boundaries in this situation? We have x equals 0, we have y equals 0, and then we have all the points along this line, which is y equals negative 3 over 2x plus 6. We can find that by setting z equals 0 here and solving for y. Now for all of these lines, we notice that the box is basically going to be completely flat. The z value will be 0. It's going to be a rectangle in the xy plane. So for all of the boundaries, the volume is 0, and that's not going to be very interesting. That's not going to give the maximum volume. So we're done with the boundary, and now we need to look at the inside region. For the inside, we use what we saw in section 13.8, so the first partial derivatives need to be equal to 0 or maybe undefined, and therefore we're going to calculate the first partial derivatives, so partial x and partial v partial y, and that's pretty straightforward. We get to these two expressions. Notice that factoring out x and y is going to be nice because we need to set these equal to 0. So we can already rule out that these partial derivatives are undefined. It's polynomial, so it's always going to be defined. So we only need to look at a situation where they are both equal to 0 at the same time. If Vx is equal to 0, that means either x equals 0, this, or the parenthesis equals 0. And for Vy, it's sort of symmetrical. Either y equals 0 or 8 minus 4x minus 4 over 3y equals 0. Y equals 0 is not inside the region. X equals 0 is not inside the region. So the only case that is inside the region that we should consider is when that is 0 and that is 0. So we set up these two equations. It makes a little system of two equations in two variables that you can see here, and with quick manipulation you find that y equals 2 and x equals 4/3. The nice advantage of having a closed region, which is inside region plus boundary, and nothing going to infinity, no open parts. The advantage is we know that to find the absolute max and absolute min, all we need to do is to plug in all the candidates, find the volume, and then we can just quickly compare. So here we find that v equals 64/9. The other candidates that we had found were v equals 0 on the boundary, so we are confident that this is going to be the absolute maximum. There's no other option. Were we to practice, or were we on an open region without boundaries, we may want to look whether this v equals 64/9 is a relative min or max. And to do that, we would use the second partials test. So we need the second partial derivatives, in which we plug in x equals 4/3 and y equals 2. That yields to finding the value of d, and we see it's greater than 0 for a vxx less than 0, and that means it's a relative max. So this is good practice, but in fact, in this case, it was not necessary because we have a closed region. In the second example, an electronics manufacturer finds that the profit in dollars obtained by selling X units of DVDs and Y units of recorders, so we have DVD players and DVD recorders, is approximated by the model here. So this is again a function of two variables, X and Y, and we are again going to have to look at the boundaries and the inside region. So first, let's sketch the domain. What are possible values of X and Y? This time, the domain is limited by common sense. We cannot build negative units of DVD players or DVD recorders. We could decide to completely ignore one of them, so we would make 0 DVD players and Y DVD recorders, or vice versa. So the domain is an open region. This time it doesn't close here, it just goes on. We could build millions and millions if that was profitable. So we noticed that the boundaries are only x equals 0 and y equals 0, and then everything else is the inside region. The relative extreme values for a function of one variable can occur in 3 different places only. One is if the derivative in terms of that one variable is equal to 0. One is if that derivative is undefined, and one is the endpoint. So this is listed here. These two are what we call the critical values, and then the endpoints is an extra thing we need to check. So first derivative in terms of y is going to be negative 0.002y plus 10, and if we set it up equal to 0, we find y equals 5,000. If we look for places where the first derivative is undefined, we're not going to find any. This is a polynomial, so it's always defined. Its derivative is always defined. There are none. Finally, the endpoint. So we are looking at the line x equals 0. We are looking at this line, and there's no endpoint as y grows, but there is an endpoint here at the origin. So that endpoint would be setting y equals 0. And if we do that, we plug in. So we have two candidates here. We have y equals 5,000 and we have y equals 0. If we plug both in, we see that making this choice of building nothing is a very bad idea. And if we choose to build 5,000 DVD recorders with 0 DVD players, then we would make a profit of $15,000. The second boundary, so this is a case where we would decide to build only DVD players but manufacture no DVD recorder. We set y equals 0 and we get a function in terms of x only. Once again, it's a quadratic function, so we can follow the same principles. We will look for where the derivative is 0, where the derivative is undefined, and the endpoints. And so the process is exactly the same. The first derivative is negative 0.002x plus 8. This is never undefined. It's equal to 0 when x equals 4,000. And again, the endpoint. So we are looking at this line here, and there's only one endpoint when x equals 0. Unsurprisingly, the profit is negative $10,000 here because it's the same point as we did earlier. Now, if we plug in x equals 4,000 in the function for the profit, you can choose this or you can choose that, it's the same. You find that the profit would be 6,000. So it's not as good to build only DVD recorders as opposed. It's not as good to build only DVD players compared to building only DVD recorders. But hopefully there's a situation in the inside region where we are building a mix of DVD players and DVD recorders, and manufacturing some of each makes the profit even greater. So the inside region, we want to set the two first partial derivatives equal to 0. Straightforward calculation to find the first partial derivatives. We set that equal to 0. We solve a small system of linear equations, and we find y equals 4,000, x equals 2,000. And in that case, the profit is 18,000. Clearly, it's better than 15,000 and it's better than 6,000, so we found a maximum. We can check with the second partial test that it tells us it's a max. So we need to find the second partial derivatives. Interestingly enough, x and y have no influence here on the value of d. This is d. Well, this is d. If we just plug these values pxx times pyy minus pxy squared, we find that it's a value greater than 0. Pxx is less than 0. It doesn't matter where we look, it's always less than 0. And we conclude that it's a maximum. So the greatest profit we can make is $18,000. Okay, so that's it for these two sample application problems. Thank you.